Okay, so croeso pawb, welcome. So Elen Parry dwi, y rheolwr ar prosiect Gwnaed o Glân. So fel ymateb i'r clystwr, rydyn ni fel prosiect Gwnaed o Glân wedi comisiynu astudiaeth i fewn i Technolegau Newydd Sgwrio Gwlân. A mae'r adroddiad ar gael ar ei gwefan. A dyma Graham Ormondroyd o'r Biocomposite Centre Bangor i egluro'r adroddiad, a bydd yna amser ar y diwedd am cwestiynau. Diolch.
There we go. Good afternoon, everyone, and welcome. But also future potential and future disruptive technologies. As Ellen said, my name is Graham Ormondroyd. I work for the Biocomposite Centre. I'll be telling you a little bit about myself, but the clicker's not working at the moment. Try again. So today I'll be telling you a little bit about myself and why I am so interested in wool, and the one teeny tiny mistake I made about 10 years ago that started this journey for me. We'll be talking about scouring as it's done today, and we'll be looking at scouring quite in depth just to see, make sure that everybody's on the page. And I'm sure here, both in the room and in the audience at home, there are people that know much more about scouring and wool processing than I do. But let's get ourselves on the same page and just see what the current industry is like. Well, if you move forward one. There we go. And then we're going to talk about some new and novel disruptive technologies. Now, I'm sure all of you have spent hours poring over a report I wrote for the Made with Wool project, and if you were like me, didn't understand any of it. So what I've decided to do is take the three concepts that we talked about in the report and essentially run a 101 course on each of them and talk about how it works and how these three disruptive technologies work, and how they may change future scouring within the UK, within the world. Finally, I'll sum up, and then, very, very excitingly for me, Q&A, and let's have that going as long as we can, if we can move forward. So, first of all, who am I? Well, as Alan said, I'm Graham Ormondroyd. I work for the Biocomposite Centre at Bangor University. I head up the materials research department there, and also I'm a reader in bio-based materials. Originally, I trained as a forester. Then I realised there was no money in forestry, so I decided to become a wood scientist. You can see where this is going. And as a wood scientist, I travelled the world. I worked in Finland, I worked in New Zealand. But eventually came and settled back here in North Wales, back at Bangor University, and started my career in running research projects. I've run far too many research projects. It's what I do now, rather than actually do science. But this has allowed us to have projects from funders as far-ranging as the RDP here, but also through to European, international, US funding, all around the idea of using bio-based materials and offsetting the use of carbon-intensive materials. And I think that's where my research in wool has taken me. But actually, it was a spelling mistake. Because I wrote one of my first project proposals. It was for a tiny piece of work. I still blame the Apple Mac to this date, but the D in wood got changed to the L in wool, and I was suddenly doing some research on the way that wool sequestered formaldehyde from the atmosphere, not the way that wood and the research that we intended. So if we can move forward. But what that led to, as I said, was European projects, knowledge transfer partnerships, Innovate UK projects, lots of commercial work. And I know some of the people out there at home I've worked with commercially over the past 10 years. And it's led to some very, very nice and actually very well-cited papers in the area of wool, and especially the one about how wool sequesters formaldehyde from the atmosphere. 2 book chapters, 2 books there talking about wool as a bio-based building material, but also this new one that came out this year on wool fibre reinforced polymer composites and how we can use wool as an advanced textile and advanced fibre in not just construction, but automotive and aerospace manufacturing. So watch this space. For my sins, I advise British wool on non-textile use of wool. I sit on the steering group for the Circular Economy KTN on their wool group, and also sit on behalf of Europe on some International Wool Trade Organization committees, and especially the Interiors Committee. So that's a little bit about me, if we can move forward. But we're here to talk about scouring and the art of scouring wool. If we go again. So I guess the first thing is, why do we scour wool? And we scour wool essentially to produce a product that is usable, and usable in the textile situation. So to produce either clothing, as some of us are wearing wool clothing today, or to produce textiles and carpets and furniture. But the scouring is there to get a consistent product for the manufacturing of these fur products. We know that, and everybody knows, wool's a greasy product, and it has lanolin, and it has dirt, both for hygiene uses, but also for processability. There's an interesting thing that I didn't realize until I was researching this the acidity or the alkalinity of the fibre has to be balanced so that you can take the dyes within the dyers, dyeing companies, and take the dyes at a consistent level. And then there used to be, when we had a big worsted industry within the UK, there used to be a need to detangle the fibre and stop the fibres matting. For the production of wool and the woolen process, that isn't as much of an issue, but that issue is still there, so the reduction of entanglement. So that's why we scour wool. If we move forward. There's a lot of factors that affect the how well the scouring works, and I've listed them here. I'm not going to go through them all. You can see them on your screen. But the amount of openness in the bale as it goes through the scouring process is very important, because if it's a compacted bale, you're not going to get the scouring liquor into the centre of that bale. The length of the scouring line and the water quality that's used, time, temperature, it's pretty obvious stuff, really. The amount of mechanical agitation of that wool within the scouring beds, and the efficiency of the squeezing presses at the end of the scouring process to remove all that liquor and all the dirt that's come out of the wool, and then move forward to the next process. So here we have a scouring line, and this is it's a very straightforward thing. And as much as I read, and we'll talk about this later, but as much as I read in the scouring literature that the process has come on leaps and bounds, in essence, fundamentally, it's the same thing we were doing 100 years ago. We're just doing it a little bit better. So I'd say there's been some incremental changes, and we'll talk about this later, but there's been some incremental changes, but fundamentally, we're still doing the same thing that they were doing in the Industrial Revolution, back in Bradford, back in Salts Mill, and at the time when this process was being developed. But what is the process? Well, you take your wool, and the first thing you have to do is, you've got to remember, you're trying to get rid of the grease on the wool. And if you're trying to get rid of the grease, the easiest thing to do is melt it. So the first thing you need to do is you need to take the wool and the water up to about 40 degrees. Lanolin melts at about 38 to 40 degrees, depending on impurities. So you take the wool to that temperature. Once you've taken it to that temperature, you submerge it in this liquor, which is a combination of water, detergents, different types of detergents, and then you agitate it. You agitate it in your first bed. You can see here. Once this water starts getting dirty, you move it to the next, and then to the next. And it's a process as you go through the whole system of moving less dirty wool into cleaner water. And eventually, whether this is a very simple four-bed system, but you can get 5, 6, 7, 8 beds, depending on, one, the quality that you want out at the end, and also actually the fineness and the grading of the wool that you're scouring. Because this can be quite a harsh process on the wool itself. If we move forward. Now, some of us recently went to see a scouring plant, and it was the first time I'd ever seen a scouring plant. Boy, are they archaic. They're scary Victorian places. They're not really that clean. And actually, I said, and please, nobody quote me on this, but it's the second worst factory I've ever went to see. The first was a leather tannery in India. But as you can see, these places are hot. You've got water at 40 degrees, open vats with this watering. They're hot, they're smelly, there's a lot of production going on, they're noisy, and they do what they need to do, and the scouring plants we've got in the UK are scouring much more than the amount of wool that the UK produces. Because if they just scoured the wool that we produce in the UK, they could not exist. But also, there's such fine margins on this that actually moving this machinery into the 21st century is going to be a struggle for them. So if we move on. So once you've scoured the wool, and this is where some innovation has come on in the current practices, once you've scoured the wool, you have your waste and your effluent. And a lot of that waste, about 50 to 60%, is wool grease. Now, I'm going to ask a question here, and it could be a rhetorical question, but what do you think has the most value coming out of the scouring? It's not the wool. Kilo for kilo, it's the processed lanolin that comes off the back of their waste effluent plant, which is worth much more than any wool that's produced in the scourers in the UK. But you have to process that lanolin, and we know that the two scourers do. And that comes together with organic components. So some of the secretions, I think that's the best word to use, that happen on sheep, and they become dried into the wool, they have to be got rid of. There's the detergents, of course, which have been used to clean the wool, and then minor components, so the insecticides, biosulfates that are used, peroxide that might have been used to dye the wool, and then the dust and the very fine particles of wool and of grass and of dirt that come out and need to be processed and got rid of. So, whilst I say that lanolin is probably the most expensive product that's coming out, also getting rid of this, what is chemical waste, also is a big cost to these factories. Scouring plants don't just have the function of scouring, they have several other functions within the wool processing. So it is where the blending of wool, so if your carpet is made from a blend of different grades of wool, that is where it happens. There's a mechanical process to remove dust prior to scouring. Any treatments that the wool undergoes, so we spoke about bleaching, but whether there's bleaching, whether a fire retardant is put onto the wool, whether an insecticide is put on the wool to prevent moth issues, that's done in the scouring plant. They also, in the UK certainly, and in Australia and New Zealand, have a requirement to test their wool for things like the pesticides, the insecticides, and give test certificates. I've already mentioned the extraction of the grease from the scour effluent, and that's done for profitability. And then, as I said, stabilising the pH so that the wool can be dyed in a controllable manner. I did mention there's been some improvements. Most of these improvements have been driven by environmental regulation. So water quality coming out of the factories. You know, it's both our scourers in the UK are very proud to tell us, and we should be very proud of them, that the water coming out of the scouring plant is cleaner than the water going in. Knowing my history of where those scouring plants are and what we fondly knew as Mucky Beck in Bradford, I have no doubt that that's absolutely true. The waste recovery and processing, that has become better over the past 50 years. And this whole idea of prevention of discharge to the environment. One of the other other innovations that has happened is that scouring has become potentially available on a small scale. And the idea that small-scale scouring plants can be bought, and in fact, I was looking only yesterday, you can go to Alibaba and get a small-scale scouring plant for about £20,000. made in India. And these are potential for artisan producers to be able to scour their own wool, but to produce wool at a very commercial scale, like our scouring plants do, your cost of your wool coming out of this plant may be £17 a kilo rather than £1.40 a kilo, and that's concerning. And that's largely because your money that you'd have to pay to get rid of your effluent would be an issue. So I took a deep dive, just off the back of having this presentation ready, I took a deep dive into the world's first full LCA on the production of a woolen garment. And I found it really, really fascinating. Technically, and we're not here to talk about LCA, but I find it really fascinating because they talk about pollution per time worn. So the graph you see here, which I'll explain to you in a minute, it's the pollution for every time you wear that jumper. There's a lot of nuances there, which I won't go into. But what's important is this middle graph here. That's all about production, but it's not about the production of wool and the scouring. It's about the production of a jumper. So it includes the scouring somewhere, but we don't have the data behind it. But it also improves the knitting and such. But you can see in production that it is as water intensive, or nearly as water intensive as growing sheep. You can see that the fossil fuel energy for production, and a lot of that will be through the scouring plant, is massive. And then the overall CO2 at the bottom there, it's about half of the CO2 emissions that come from the farming of a sheep. And we all know that why there's CO2 emissions from sheep, and it's the methane, and I'll leave it at that. But it is very hard to get clear and precise data, and it's something that we want to do if we can find an MSc student to come and do it. So again, please, if anyone wants to do that. And a lot of LCAs are based on very, very specific products. So the one that I was reading, a jumper, and as I say, on wearing a jumper. There is a need, and if we want to push forward with some of these novel scouring and these disruptive scouring ways, there is a need to understand the baseline and understand the actual environmental burden of just purely doing that one process. So, to talk about the new and novel scouring techniques, as I say, I hope you've all read the report, and I won't have to speak too long, but we'll go forward. So one of the most exciting novel scouring techniques that I found was the idea of using ultrasound. Now, ultrasound simply is sound at a frequency which you and I can't hear. So you can see the chart on the screen there. You move from about 20 hertz up to 20 kilohertz, and that's about what you and I can hear. I hope my hearing and your hearing is as good as it can be. You just go above that, and that's what your pet dogs can hear, and that's why you can have a silent whistle for your dog. When you go from about 20 hertz to 20 kilohertz to about 40 kilohertz, that's when you start having the potential to cause damage and cause destructive effects. You go massively above that, so you go into the megahertz range, and that's when it gets exciting for the medical people, and that's when you can't start bouncing these images off babies, for example, and they'd be absolutely fine, and that's where you get your ultrasound scans. But where we're interested in the 20 kilohertz through to about 40 kilohertz range. So it's the stuff that can be destructive, but using it in a way where it's destructive for moving things about and moving the grease and the dirt off the wool. So the way this works is you turn this sound energy into mechanical energy. And you do that by using a transducer on water or on a detergent, on a liquor, and you vibrate the water. And if you vibrate the water at these type of frequencies that we're talking about, you start to create very, very tiny, but very, very strong bubbles within that water. And if you're creating those bubbles can move about in that water, and they get very, very excited, and they get in between the grease layer and the wool, and start pushing that grease layer off the wool. And so this is how we start to separate the wool and the grease within this water that's vibrating very quickly. Now, I run a lab and I mess things up and things get very dirty, and we do throw it in an ultrasound bath, and we can take things that scrubbing and cleaning just doesn't happen, and these microbubbles are so strong that they push off that dirt and grease. Move forward. So this is really exciting, and there's actually been some good science done on this, and out of the three that I'm talking about today, we see the good science. But why I get really excited is you can see, of course, on your left as you look at the screen, that as you wash, as we were talking about in traditional scouring techniques, going from one bath to the next, and the water being dirty and then cleaner and then cleaner and cleaner, it is the same when you're using ultrasound. It's just, it's a little bit better. And you can see from that graph, the black lines or the very dark grey lines, they're the brightness and the whiteness of the fibre as it comes through the scouring system. And you can see in every case, it's better with ultrasound than without ultrasound. That's great, and we like that. But where I get very, very excited is graph B. Because let's forget about the stuff without ultrasound, because we know that with ultrasound is better than without. And we look at the two graphs, the black graphs and the stripy graphs, the zebra graphs. And as you can see, on the left of that graph there, we used sodium carbonate as an agent to help clean the wool. In the middle, we used sodium carbonate and a detergent, and that was slightly better. But on the right of the graph there, you used only water. So this is water and ultrasound. And that gave us the best, or gave these researchers, I say us in the scientific sense, that gave us the best results. So that's exciting. That means that you don't need to have to process detergent for water, because using ultrasound gives you a better result than using any detergents and ultrasound. And what you can also see, and what I also find very interesting, is that you're only within... what I can see very interesting is here is the stripy graph. You can see from the top is the use of ultrasound, but at 50 degrees C water. The black graph is ultrasound at 35 degrees water. There's a 15-degree difference between those two experiments, and it's still better with the lower temperature. So not only do you save on your waste effluent treatment, but you also save on your energy bills. And 15% energy, that is significant, especially in today's energy crisis. If we can move on. So as part of a report, and you'll have seen this already, we looked at a SWOT analysis, strengths, threats, opportunities, and weaknesses, but not necessarily in that order, analysis. And you can see that there are lots of strengths. You'll have read the report, I'm not going to go through them all, but it's an energy-saving process. It's a continuous process, so it works as scouring works today. There's no enzymatic or potentially there's no detergents used. We'll come on to onto enzymes in a moment and some of the potentially good and potentially issues we've got there. It's certainly a very green process. The production of these sound waves and the production of the cavitation bubbles is not an energy-intensive process. But again, there's poor information, and this is what we're talking about, all these processes that I'm going to talk about this afternoon. There's poor information out there, and there's poor information to us academics, let alone people that want to start factories. The potential of low profitability within the scouring industry would mean the injection of money, and this goes for all of what we're talking about, the injection of money for R&D and investment. You don't see a good return on your pound, and I hate to say this, but the governments won't see that good return on their pound necessarily. Again, commercial acceptance. I talk about this for all three of the processes. It's kind of like you can have a Ford Model T in any colour as long as it's black. We know how to make them black. We know how to do scouring. So when it will be accepted and when commercial companies will want to put money into this. And there still is a reliance on energy prices, of course, because the process uses energy. So that's ultrasonic scouring, and this, for me, was the process that had the most science and science based in wool. And there is certainly potential there. Move forward. So how will we move forward with ultrasound scouring? Well, parameters still have to be refined. There's a lot of data out there about everybody wanting to do their own ultrasound scouring slightly different, and finding that sweet spot for our wool types. And I think that's an important point to know, is that scouring Welsh mountain sheep's wool compared to scouring merino wool is a very, very different parameters in the same process. This move to cooler temperatures and where the process stops being more efficient as you get cooler is something that needs to be explored. But then we get into what it is. It's all about the investment, and it's the same for everything. The investment into a pilot study to see, can we scour 100 kilograms at a time? Can we scour 1,000 kilograms at a time? And that really does need government investment into demonstrator projects. Move forward. So we talked about using ultrasound, and that was very exciting. And then we started looking at the use of enzymes. So enzymes are things that catalyze the breakdown of something. And these have been used to help scour wool. And again, the process is very, very similar to the traditional process, but you just don't use detergent. You use these enzymes, you use lipases, you use proteases, which we'll come on into a minute. But you essentially do the same thing. They're just breaking down the grease and preventing entanglement by a different means. The research on this is all still very, very lab-based, and it very much is, people in white coats doing things on a very, very small scale. But there is a lot of academic publications in this area, so there's lots of potential for it to be seen. So I mentioned two enzymes, and I'm not going to bore everyone with this, but very interestingly, lipase, this is the enzyme that helps to hydrolyze and to break up fats. And we have lipase in our stomachs, in our skin, in our mouths, but also plants produce it, insects produce it, mold and fungi produce it. So we can produce lipase, which will help break down the fats around the wool. Now, lipases are really, really interesting because they only work if they're in contact with both the oil and water. So we still need to use water in the process, and we still need to use a lot of water, which then needs to be cleared up. But on that oil and water interface, that's when the magic happens, and the lipases very specifically find an area of the fat that they know and they can see, and then they go and break it. And as that fat chain starts to break up, then it starts to fall off the wool fibre, releasing the dirt and the other things that it's holding there, and then it's in suspension in the water. Again, you have to then clean your water. As I've said, they are very, very specific, and they're very specific not to a type of fat, but also to a connection within that fat. So it's a molecular connection, and they'll only go and break that single connection up. So there's a lot of work, and there's a lot of work being done in the Centre for Environmental Biotechnology in finding these very specific enzymes to go and break up certain areas of fat molecules. One of the problems that you've got with lipases is that you still need to do this at temperature. Except the molecules, the organisms that create these lipases don't like the temperature. So there literally are adventurers out there who are going to find in hot environments, and those hot environments could be the Sahara Desert, they could be on the edge of a volcano, but they're going to find molecules that produce these enzymes, but do it at high temperatures. So we can then do it within commercial processes. I mentioned proteases, and these are enzymes that break down proteins. And these have been studied for scouring wool, but for preventing wool felting in the scouring process. And we spoke about this when we spoke about the traditional scouring methods. And this certainly is needed, but for the woolen process, not as much as for the worsting process. Now, I giggled when I wrote this because these enzymes are very promiscuous. They're the exact opposite to lipase acids. They just go for it, and they go and hit any protein that they want and break up any bond that they want, and they're happy to do their job. There are one or two that are a bit more selective in what they do, but even the selective ones generally just go and do their job. That's why these can be quite troublesome for you and I and for animals. So the handling of these has to be very specific, but as long as you specify the right enzymes, then you get the job done. And very much so, you get the job done in a very, very bio way. So once again, we did a SWOT analysis, and a lot of what we talked about, especially the weaknesses, a lot of the weaknesses is the same with ultrasound. It is a pure green process development. Again, it's easily scalable, it's scalable and potentially usable in traditional scouring factories. There's a potential to co-locate, so biotech is a massive thing in the UK, and the production, as I said, we have a Centre for Environmental Biotechnology in Bangor. The discovery and the production of these enzymes and the organisms that produce them is very much a big research area within the UK. One of the slight weaknesses is, though, that whilst you have to buy your detergents, they're very cheap. Buying your enzymes is more expensive at the moment. But we are massively in a chicken and an egg situation, where if there is a demand, production can be done at less cost. Production facilities can be set up rather than being pilot-scale lab facilities, and the cost will come down. Because the biotech economy is so big, and there is a lot of research, there is a chance, and there will be regulation about the use of organisms and enzymes. And sadly, that's just a watch this space situation. But it is a potential for scouring wool. So, my favourite subject now. Critical CO2, supercritical CO2. I'll explain what that is in a moment. But we have a lot of CO2 in the atmosphere. And we've got a lot of CO2 being given out by industrial processes, especially one that's very close to my heart, the brewery industry. So you could use CO2 in a special way that it becomes a solvent. And it becomes a very, very special type of solvent. And what you can do is use this simply to dissolve the grease and take with it all the dirt, all the other things that we've been talked about with the grease away from the wool. You can then reprocess that waste liquor. And because of what I'll explain in a second and how you can change how critical CO2 works, you can then keep parts of the grease dissolved and then drop out other parts of the grease, or drop out the dirt, drop out the grass, drop out the poo. But then you can take what is a homogeneous grease and then you can split that into its separate components. And suddenly that becomes very, very interesting, especially when you want to get rid of the solvent. Instead of using traditional solvents and have to go through long cleaning processes, you just release pressure and poof, it turns into a gas, and you have a very, very ultra clean product. This is why critical CO2 is more and more being used in the medical industry, in the food industries, and why now, the first picture that you saw when we were talking about the novel scouring, that was a critical CO2 plant. So this has been done on a massive, massive scale. If we move forward. So you'll have all seen this and understood this in the report, I think, so I won't dwell on it again. But essentially, supercritical fluids are very simply something that's held at a temperature and pressure where it can't decide whether it's a liquid or a gas. So it's something that acts as a liquid, so you can wash with it, but if you put it into a room, it will fill that space as a gas does. And that makes it very, very exciting for, as I say, cleaning wool. The other reason it's exciting is this area of supercriticalness is if you change the temperature or the pressure, as I said, you give it different properties. And that property could be its pH, it could be its polarity, and that will dictate what you can dissolve and what you can drop out. So it's really, really interesting. If we move forward again. So I've kind of talked over my slides a bit, but this is the process. And as I already mentioned, you feed your wool into the reactor, you fill it with supercritical CO2, you then set the pressure and temperature to dissolve the grease and the dirt that's in there, and then you pull that out, and you can move that out very easily. So that's where you've got your wool. That's what we're interested in today. You've got your very clean wool there, and you could potentially just release the pressure, the CO2 will become uncritical, turn back into a gas and go, and then you have a solid waste. But that's not particularly saleable. So then, as I said, you redo this process again and again and again and again until you get your components out and the ones that you can sell, until eventually you've got the stuff that's worth nothing, and then that goes as fertilizer or fuel. If we move on, I think we've got the, yep. So once again, this process it can be continuous, it can be batch process. It does save a lot of energy. It uses a waste byproduct. As I say, quite literally our bottled CO2 comes from the brewing industry, and it's, again, it's not quite as expensive as beer, but it's, at the moment it's getting there. You get very pure byproducts. What is exciting about this is the consumables cost is cheap compared with traditional scouring, compared with certainly bioscouring. So the consumables are very, very cheap. You need the CO2. And actually you can recover the CO2 when you release it and recompress it. But where this system does slightly fall down is the capital expenditure needed to set up a critical CO2 plant, because you're working at very, very high pressures. So everything needs to be triple boilerplated and safe. And so that costs money. It is reliant on the cost of low-cost CO2, but I think that's pretty much a given, certainly in my lifetime. And again, we go through the whole idea of the potential for regulation and commercial acceptance of this new way, this new disruptive way of scouring. So they're the three most disruptive ideas around novel scouring. As I've already said, scouring hasn't really fundamentally changed over the last 50 years. There certainly hasn't been disruptive technologies. There's been improvements, as I've said, because of environmental regulation, the cost of power, the cost of chemicals, but also changes in downstream processing and how downstream they want their wool delivered. Go again. All the three technologies we described today really are in laboratory based, and they need more investment to move on to pilot scale. I think this is something called the technology readiness level. I won't bore you with where it came from, but this is a way to describe how where technology is and how long it will take to get to market. I think with all these three technologies, we're only here, TRL 3 or 4. I don't think we're any higher. We've not seen demonstrated plants. We've not seen pilot scale production of these, but it could happen. It needs the investment, and that's what I'm trying to do. It'll keep me in a job until I can retire. And on that note, I think if we just check, that's me finished. Thank you very much for listening.